It's very exciting to have Eugene Demler as our last speaker of today before we head over to the poster session. Eugene's going to really talk about the physics problems that motivates trying to look at innovative approaches to data, less about like specific machine learning methodology, but really about what's motivating us. And I think that would be really perfect. Get you guys all fired up, thinking about different problems, challenges, and be excited about learning. So without further ado, and Eugene's now at Harvard and ETH Zurich, which is new as affiliation. But on his way to ETH, he agreed to give this talk while packing. So I'm really grateful that he's agreed to give this talk. So let's welcome Eugene. It's all yours.
Thank you, Una. So first of all, I want to express my sort of gratitude to Una for organizing this wonderful meeting. It's really very timely. And she succeeded in bringing together very exciting talks. I learned a lot from talks in the morning and look forward to more talks and discussions in the afternoon. So as Una said, I consider my goal to connect some of the discussions you guys heard earlier today with advanced tools of machine learning to more traditional approaches in physics, which is analysis of correlation functions. And as you will see, throughout the history of the field of cold atoms, like experimentalists have been building up while in collaboration with theorists to look at more and more complicated and sophisticated correlation functions, so that sort of doing pattern recognition, doing tools of machine learning becomes a natural next step. So the work I am presenting today was primarily done by young people, Fabian Grusten and Abel Bort, and also the latest work was done in collaboration with Cole, Miles, and Una. And I will also mention some of the much earlier work, which I think is what sort of got me started in the first place, thinking about sort of beyond traditional paradigms of two-point correlation functions that dominate condensed physics. So this is the work done with Yehud Altman, Anatoly Polkovnikov, Vladimir Gritsov, and Takuya Kitagawa. And I'll acknowledge along the way what made this work particularly exciting is collaboration with experimental groups of Emanuel Bloch, Markus Greiner, and Jörg Schmidt-Meyer. Okay, so okay, yes. So this is an outline of my talk. First, I'll give you a brief reminder of the whole idea of quantum noise, and then we'll talk about how it is used to do Henry-Brown twist type experiments in cold atoms to explore different new types of order. Then we will switch more to experiments on quantum gas microscopes, and this will lead us to discussion of spin charge separation in 1D, analysis of magnetic polarons in 2D, and the new insights that we recently got into the 2D Fermi-Hubbard model by analyzing the snapshots, and then at the end, this will connect naturally to the idea of looking at patterns and using convolutional neural networks. Okay, so the first part that I'm going to talk about is analysis of noise. And let me remind you something very basic, which you should remember from your first class in quantum mechanics. So consider a single particle Schrödinger equation, like one-dimensional Schrödinger equation. You have a wave function that depends on one coordinate, but when we measure the position of the particle, we collapse it to an eigenstate of the position, right? And so we collapse it to any of the points as shown here, and we can use the wave function to predict probabilities to find a particle at a given site. But in a result of any individual measurement is different from what we're used to, from what we define as an expectation value, right? So just as you recall from kind of basic quantum mechanics, the expectation value of x, right, is the first moment of the distribution given by the wave function, but we can also define higher moments. So this idea is very simple, but as you will see, it actually is very powerful for looking beyond like single particle Schrödinger equation, and it underlies a lot of discussion of many-body states that you already heard and that we'll consider today. So, and let me also remind you that, like again, in the case of the single particle Schrödinger equation, like what we could do, right, we could measure the position of the particle many times, right? What this, of course, requires is preparing exactly the same state, doing the measurement, and then what we could also do is to record like basically how often we measured the particle at a given position, and this allows us to construct a histogram of the measurements, and this gives us the kind of psi squared, right, the probability distribution of finding a particle at a given position. But this idea that actually we can get some information about the quantum mechanical wave function, not just in the expectation value, but also in fluctuations, say second moment, or even distribution function, is of course not special to quantum systems. Even earlier for a classical system, this is what was suggested earlier on by Henry, Brown, and Twiss, where they asked a very simple question. Well, consider that we have two incoherent sources, right? In that case, they were thinking about two distant stars, so like two edges of the same star. And then they're sending light signals, but these light signals are not coherent with each other. So can we see any type of interference between these incoherent sources? Well, as you know from basic wave optics, if we put a single detector, there will be no interference. But what they realized, and what is now called Henry Brown-Twiss experiment, is that one should take two detectors and measure correlations in the coincidence counts, right? And these correlations will actually oscillate as a function of relative position. So, in fact, this technique is now used as a tool in astronomy to measure, let's say, the angular size of stellar objects. And I'll not go through the classical theory, but just to connect to quantum mechanics, let me remind you like the quantum interpretation, which is due to Glauber. So he said, well, think of two objects, like two sources which are sending photons, and then we also have two detectors. And then we can, when we measure two photons, right, in detector 1 and 2, it could be that we had photon from the first detector arriving, from the first source arriving at the first detector, from the second source arriving at the second detector, or vice versa. And these are quantum mechanical amplitudes, and then depending whether these are bosons or fermions, we have to add these amplitudes or subtract them, and that will give us a plus or a minus sign. And so actually, I'll show you some of the results on this Henry Brown-Twiss experiment with cold atoms, but this actually has been quite an exciting area of research in the last couple of decades, which, okay, will not be able to do full justice to. Okay, so let me talk about perhaps the simplest type of experiments in cold atoms, and this is time of flight experiments. So it looks like there are two questions. Is it questions in the chats or? I see. No, okay, this was just
not yet. Not yet.
Okay, good. Okay, so time of flight. So think about it that we start with a quantum mechanical state. You know, this small dot is basically a many-body state of atoms. Then the confining potential is removed. Atoms are flying out, so the cloud expands. Usually, it also falls under gravity. But what's important to us is that as it expands, velocities or momenta of atoms are mapped into real space positions. So when our experimental friends take an image after the long time of flight, they take an image in real space, but we should understand it as really measuring the distribution of original particles in momentum space. And this is an example let's say, this measurement in the state, which is called the mod state, where you have individual atoms localized in the walls of the optical lattice. So think about it just like with standing waves of laser, like with laser beams from extending waves of light, there is some potential, and then it's so strong that atoms get localized. So then we do the time of flight, and what we see in this time of flight, well, we see that actually a fairly broad distribution in momentum space, which is very natural because atoms were localized in real space, and therefore, if like the usual uncertainty principle means that therefore there was large uncertainty in momenta of the particles. But if you take a cross section of this image, and this is an actual cross section, you see that it's not like a perfectly smooth line; it has some wiggles in it. And so the idea that actually first Juho Daltman started thinking about was, well, what if we analyze not just the average density, but let's look at correlations, meaning we will not ask a question of what's the density at point 1 or a density at point 2, but rather if we know that there is like an increased density in a given shot at point 1, what can we tell about the change in the density at point 2? And formally, this is defined as second order correlation function. And so this is actually, okay, I'll sort of skip theory results, but these are results of experiments from Emmanuel Bloch's group. So this is, if you take the Bloch state if we take the mod state of bosons, this was an original image. If we measure correlation functions, we see that in the correlation functions, there are very sharp peaks. And this is actually, and if we convert these peaks into momentum, I remind you, it's time of flight. So real space image corresponds to momentum in the original quantum mechanical state. So therefore, these distances can be converted into momenta. This momenta just correspond to reciprocal lattice vectors. And the fact that we have correlations is exactly Henry-Brown-Twiss experiment, this sort of extra plus sign. And physically, we can think about this way, or eigenstates in a lattice, they correspond to superposition of states which differ by reciprocal lattice vector. So if we measure like a physical atom at momentum k, there's an enhanced probability to find another boson at the same reciprocal, at the same eigenstate of the lattice, but that eigenstate can differ by reciprocal lattice vector. And when they did the same experiment with fermions, again, if you look at the image itself, it's very hard to even see the difference between bosons and fermions. But in the correlation function, you see a minus, you see anti-correlation, you see dips, and this shows that we're actually doing with a fermionic Henry-Brown-Twiss. And this is actually has now become even a tool for detecting many-body states of cold atoms. So this specifically is an experiment from Marcus Greiner's group. So in the tilted lattice of one-dimensional bosons, they actually managed to realize a very interesting checkerboard phase, which had occupation of 202020. And okay, you heard about quantum gas microscopes, but unfortunately, at that time, they did not have, they had kind of resolution that was subject to constraints. In particular, they could not distinguish two particles on one side from zero. This is just an artifact of detection. And so what this means is, experimentally, it was hard for them to really see directly this sort of pattern of 202020. So what they did instead was to do time of flight experiments and measured exactly this noise correlation. And you see this additional peak. This is very much what Uno was telling you during the last lecture, how X-ray works. If you have some kind of charge density wave, you change the size of the unit cell, right? If you double the size of the unit cell, you get additional reciprocal lattice vectors. And here you can see this reciprocal lattice vector showing up in noise correlations. So again, I emphasize now, it does not show up in the average image. It's not something you get by averaging over many shots. You really have to analyze correlations within individual images. Any questions about this? Okay, then let's move on. So now let's talk about another type of experiments, which are interference of low-dimensional condensate. So this is a field with long history. In fact, this was some of the earliest experiments with BEC. like say done by Ketterler's group, what they did was to take two three-dimensional condensates, which did not have a well-defined phase coherence between them, and let them interfere. And this seems surprising. Like usually, if we look, like remember what you learn in optics and then like in basic quantum mechanics to see interference, well, you have to have actual coherence. But here we prepared two condensates which do not know about each other. There is no phase coherence between them. So how come we get interference fringes? That's what actually comes out of experiments. So the conclusion that the understanding that people arrived was, well, that we should think about this as, okay, we get an interference pattern in every shot. However, we cannot predict where exactly these fringes are going to be. The position of the fringes are random. And that's why if we average over many shots, we will get zero, but in an individual shot, we will get finite fringes. So we'll talk more about how to understand this later on.
Eugene,
now,
there was a question.
Yes. Mm-hmm.
Can we gain more information with higher order correlation? I think
it's coming. Yes.
Yeah.
This is coming.
That's coming. Exactly. Okay. That's the answer.
Yes. So, right. So, but in the experiment that I showed you earlier was like three-dimensional condensates, which do not have a lot of internal fluctuations. What people have done later was to take condensates in reduced dimension, like 2 and 1 dimensions, where we know that there are like at finite temperatures, there is no actual long, like kind of macroscopic coherence. And so when so think about, say, these two pancakes. And when we do interference, in this case, we let atoms expand, they expand primarily in the transverse directions. So again, we get this interference patterns, and the position of the fringes tells us about the local phase difference. And you see that the phase that these fringes are meandering tells us that this phase difference was fluctuating. We can see the same for one-dimensional systems probed in Schmidtmeyer's group. So again, these are kind of interference images from two tubes. And then when we image, we see this meandering interference fringes. Okay, so how do we think about these experiments? Well, I'll give you a kind of very rough picture. Think about atoms coming from the first condensate and the second condensate, and now we let them expand. So we measure the wave function psi, like at point R after the expansion, and I can write it as a superposition of atoms which came from the first condensate and the second condensate. Then we take the density, which is psi squared, and it has a cross term. And now we can relate the wave function, say psi1, to the original phase of the condensate and just ballistic expansion, like expansion of free non-interacting atoms. And this will just give us some factors which have to do with the distance between the condensate, like position. Basically, we can say that, oh, it's kind of like if we know that we measured an atom at point R and after time t, then we know the velocity, right, with which atoms had to travel. And so this gives us a momentum, which is this md over t, and then it's plane wave, so k times r, and then there is a phase difference between the two condensates. So if we now measure the average density, right, like, so obviously we will get zero because for two independent condensates, there is no expectation value of the relative phase. However, if we measure correlation, the correlation function between the two densities, we see that we get oscillations. And that's exactly how the argument which you heard before, it shows that, okay, if we, we know that if there is a kind of a local peak in the density, it will be followed by another peak because the density is oscillating. However, we cannot really predict in a single shot, in any given shot, whether at a given point we'll have a maximum or a minimum. We just know that maxima should repeat themselves with a certain periodicity and minima should repeat themselves with a certain periodicity. Okay. So now what we can do is we can think about extending this argument to systems which have internal fluctuations, say this one-dimensional condensate. Again, so like by the same token, if we look at the local interference fringes, we see that it depends on the relative phase between the two condensates at a given point. And now what we can do, we can just integrate this interference fringes, but notice that for fluctuating condensate, these fringes will not be in phase with each other. So when we add them all up, they sort of partially cancel each other. And or more formally, what we do, we sort of take the amplitude of interference fringes squared, but notice that this is amplitude of something which has already been integrated. And so we write it as a now kind of each operator, right, is an integral. Now we take an expectation value of this. Now we have 4 operators in here. And you see that it, for independent condensates, it nicely separates into a product of correlation functions within individual condensates. So therefore, by measuring this fringe contrast, like in this interference experiment, we're actually probing independent, well, measuring correlation function within individual condensates. Okay, and for again, we do not have time to talk about details of 1D physics, but I'll just briefly point out that in 1D, at finite temperature, correlation functions should decay exponentially with a length scale set by the temperature. This is just a usual sort of Boltzmann-Gibbs thermal equipartition. You have KT for every degree of freedom, but at 0 temperature, we have power law decay of correlation. This is a so-called Lattinger liquid. And so now let's say if we take 0 temperature correlation function, which is a power law, we can plug this into the amplitude, and we see that the amplitude of interference fringes, okay, depends in a rather non-trivial way on, say, the system size. And the way you can probe this experimentally would be, well, okay, we take our images, right? And then we can look at fringes by integrating over different length scale, over shorter segments or over longer segments. And we see that the dependence of the fringe contrast on the length should follow this dependence. Well, unfortunately, this turns out to be hard for experiments that have been studied, say, in York-Schmidt-Meyer's group, just because the Lattinger parameter turns out to be very large. And so corrections to just what we would get for non-interacting atoms would be small. However, this is where the argument came in that somebody was asking about, oh, what about higher order correlation functions? So what if we start looking not just at, say, we saw that fluctuation in the fringe contrast reduced to 2-point correlation functions, but now let us look at higher moments of the fringe contrast, and this naturally reduces to very high order correlation functions. In fact, we can ask even a more sophisticated question, ask what about the full distribution functions? And that is something that you, okay, well, just maybe before I show you results, just tell you how experiments are being done. So the way experiments are done is, this is a result of a single interference pattern. You see, okay, in this case, actually, this is a fairly good pattern. It has a relative phase, right? It has an amplitude. So you can analyze it and extract. So the amplitude is like a radius, and the position of the fringes is a phase, right? And then what you do, you start doing this experiment many, many times. And sometimes, let's say, so like often the fringe phase, right, can be, will fluctuate. Sometimes the contrast will be reduced, but we accumulate statistics, and at the end, we will get the full distribution functions. And so this shows you now like what you can get. So it turns out that you can actually analyze full distribution function of fringe contrast. And I have to refer you to original papers for details of theoretical analysis and experiments. But the bottom line is that from 2-point correlation functions, we could not see that we were dealing with a Lattinger liquid. But when we look at full distribution function, which means we're analyzing high order correlation functions, we could verify that we're dealing with an actual Lattinger liquid. And so in particular, for short segments, when we're primarily, when thermal fluctuations are not pronounced yet, we could see very special Gumbel type distributions of the fringe contrast. So this is sort of the answer to the question, what can we learn from higher order correlation functions? Well, we can learn, like in equilibrium, that this is a true Lattinger liquid. And then there was an interesting follow-up work which used the same tool analysis of distribution functions to analyze transient dynamical states. Again, if there are questions, I'll be happy to talk about this afterwards. Any questions, urgent question at this point? Yes, it looks like there is a question.
Oh, thank you so much. I have a question about the page about the gas experiment figure. So in that case, you showed there is some fluctuation in the z-axis, and it shows the kind of fringe in the result. So I was wondering how it can be related to the this kind of thermal fluctuation, because the 2D material fluctuation should be displayed in 2D in my guess. So
this is 1D. So in this case, we're dealing, but this only makes fluctuation worse. But the idea is that you literally, what you do, you use the fact that, if we look at quantum fluctuation, right? So remember, I showed this correlation function, this 2-point correlation function. At finite temperature in 1D, it decays like exponentially. At 0 temperature, it decays as a power law. And then, there is a more complicated formula which gives us interpolation between power law and exponential, which is what you need to get this more general expression. So does it answer your question?
Oh, yeah, thank you so much.
Okay. Other questions? Okay, then let's move on. So now we will move to optical lattice systems. And here the central idea is that hopefully most of you know that there has been a lot of work aimed at understanding the Fermi-Hubbard model. So in this model, we have, which we believe describes this complicated family of materials, which has obviously a lot of chemical elements, but for our purposes, let's just take it as a fact that a lot of relevant physics can be described in a model where we just have fermions hopping between neighboring sites, and this is described by this first hopping term, and then we have local on-site repulsion. And this is the type of model that can be realized with ultra-cold atoms in optical lattices. And an extra advantage of the optical lattice emulators is that parameters can be controlled independently. So we can separately control the hopping of fermions and interaction between them. There is also a model which is a very close cousin of the Fermi-Hubbard model, because in most cases we're dealing with U, which is fairly large, which is, let's say, 8 times the hopping. So then doubly occupied sites are very unlikely. But what we can do, we can sort of eliminate them through perturbation theory and derive a model which is called the TJ model, in which now hopping is constrained on not creating double occupancies, but then we have anti-ferromagnetic superexchange. Let me just, for those of you who are not familiar with the origin of superexchange, let me just explain the argument. So imagine that we have 2 fermions on neighboring sites, right? And then if their spins are anti-aligned, well, then at least as a virtual process, one of the fermions can go to the neighboring sites, right? This creates a double occupied site, which has energy U, but okay, it's still an allowed physical state. And then one of the fermions comes back. And this, and the fermion which comes back doesn't have to have the same spin as arrived in the first place. Therefore, this process can contribute exchange type term, right? So when we have a spin on the left is flipped from up to down, and the spin on the right is flipped from down to up. Or at least, even if there is no spin flip, at least there is some lowering of energies when spins are anti-aligned. On the other hand, when spins are aligned, then we notice immediately that doubly occupancies are just not possible by Pauli principles, and therefore fermions cannot regain any kind of kinetic energy. And so therefore, you can do the simple perturbation theory and realize that you can capture this physics by saying that when we have 2 occupied sites next to each other, there is anti-ferromagnetic interaction between them that scales as t squared over U. So that is what we put into this TJ model. We said, oh, well, we eliminate double occupancies, but we take it into account virtually because it gives rise to this anti-ferromagnetic superexchange. And what has been a real game changer in the last 5 years or so is that our experimental colleagues started doing experiments with optical lattices where every particle in the many-body wave function can be measured simultaneously. So we're really sort of getting unprecedented data about many-body systems. And obviously, it comes in now as sort of images, and therefore it's natural to think about sort of more data science inspired ways of analyzing them. And that's what hopefully we'll discuss at the end. But like, let me start with a kind of more the way people started thinking about this analysis of the system, starting from the conventional standpoint. Okay, so the first question was, well, okay, if we're exactly at half filling, there is one particle per side. That's where we have antiferromagnetic state. So can we characterize the onset of this antiferromagnetic order, just classically anti-aligned spins? So the first thing they measured was just 2-point correlation function. So this is a result from Marcus Greiner's group. And like on the right, you see high temperature data, right? And you see that correlations, and these are already sort of spin correlations, just the usual two-side spin correlations, but the alternating sign has been taken out so that it doesn't oscillate. And you see that we have weak oscillation at high temperature, but as temperature is lower, the correlations functions get stronger and stronger, and they become more longer and longer range. So here you can see the correlation function, how it diverges at 0 temperature. Exactly as we expect for a two-dimensional Heisenberg model. What is actually, again, special with cold atoms, right, is because we get an image, we can analyze not just 2-point correlation function, but we can analyze also high-order correlation function. And in particular, we can talk about full distribution function of staggered magnetization. So, and you can see that not only the kind of the 2-point correlation functions change, but also high-order correlation functions change. In particular, you see that they sort of like, to begin with, essentially that there is a lot of self-averaging. So staggered magnetization is just very close to 0, whereas at the lowest temperature it becomes much broader distribution. And in fact, you can already start checking that like simple thermal fluctuations would not be able to account for this physics. You really have to take into account like kind of quantum nature of spins. So you have to look at quantum Heisenberg model rather than the thermal one. Okay, so the next interesting step was done by Manuel Bloch's group, and this was an idea to analyze one-dimensional system. So let me just give you sort of a very brief overview of how to think about spin charge separation in 1D. So in 1D, it turns out that when we take fermions, we have antiferromagnetic interaction, but we cannot have broken symmetry. So as a result, the state should be really thought of as a combination of short-range singlets. So all kind of spin 1/2 fermions are bound into singlet pairs, which are fairly small. Now imagine that we remove one of the fermions, like here we have an empty side. But what this also does, it creates an unbound spin 1/2, right? Because it used to be part of, let's say, spin singlet configuration, but now kind of the partner has been removed. And what happens is that if we let like this configuration to relax, so even if we let it reach the ground state, what will happen is that this sort of object, which is an empty side, and an object which is just unpaired spin 1/2, they separate, and now they can propagate separately. And this is what is called a hole-like soliton, like a holon, right? It's sort of relative to the ground state. See, the charge has changed by 1, but like in the ground state, all the spins were paired, so there was no kind of extra spin. So here, this extra configuration only carries extra charge, so it's a holon. And then there is a spinon, right? This extra object, it also has a charge 1 per side, but there is an unpaired spin. And this is spin 1/2. And what people realized early on is that if you look across the holon, for example, then actually spin correlations look as if this holon was not there. We just have to remove the side with the holon. So in particular, on the kind of, if we compare spin correlation of two sides, where one side is on the left of the holon, the other is on the right, they're most likely to be antiferromagnetically correlated. They make a singlet with each other. And this is very different from, let's say, the system where there are no holes, right? Because now we're looking at sites which are two lattice sides away from each other. So in a perfect antiferromagnetic state, they would be ferromagnetically correlated, but now they become antiferromagnetically correlated. So somehow there is a kind of like, technically we often call it like a domain wall across the soliton. But in fact, one can prove an even more general theorem that when we take this kind of 1D Fermi-Hubbard models at finite doping, then what we can take the many-body wave function and remove all the sides. And when we remove all the sides, we just end up with sides where there are spins, and the wave function on this squeezed space should be the same as if holes were not there. So somehow in squeezed space, spin correlations are the same as at half filling. And but of course, to just think about such measurement, you have to be able to know what's happening on every side, and that was not or was accessible in traditional solid-state systems, but that's what can be done in cold atoms. So this, and this is actually shown like beautifully in this data from the Bloch's group. If you see, when they look at just the usual two-point correlation functions, so at half filling, you see that, okay, nearest neighbor have antiferromagnetic correlations, and they become ferromagnetic, then they become again antiferromagnetic when where sites are sites away, and so on. But as soon as we start doping, like this oscillation of spin correlations are washed out very rapidly. However, when they take like their snapshots, see, like in their snapshots, they can actually see where there is a hole, right? So like here, you can actually see a position of spin downs and spin up, like they're imaged separately. So they can remove the sites where there were holes and look at spin correlation in squeezed space. And now in squeezed space, correlations are the same regardless of the doping. So is there a question? No? No, okay, it's still the same one. Okay, any new questions? Okay, if not, let's move on. So, so we talked about 1D, now let's talk about 2D. So in 2D, dynamics of a hole in an, let's start with the same construction. We remove one fermion and we start it in a state which has sort of the best seemingly kind of spin configuration. And in 2D, it actually happens to be essentially classical spin configuration. And what you notice is that as the hole propagates, it leaves behind a string of flipped spins. You see, like when the hole moves to the right, the spin down sort of is displaced where spin up used to be. And so as a result, magnetic energy goes up, right? And the more the hole propagates, the longer is the string of flipped spins. And that's why this sort of hole construction is often called geometrical string picture. So people realized this argument very early on. And so there were even ideas that if we have a hole in an antiferromagnet Mott insulator, at that point people talked about antiferromagnetic semiconductors, there should be a ferromagnetic island around the hole. Well, we will see, actually now it's believed that this happens only for some extremely large values of U, which are not relevant, say, to cuprate physics. But there is a very non-trivial interplay between spin and charge degrees of freedom, and that's what we want to discuss today. So a very useful way of thinking about what happens for kind of doping two-dimensional Fermi-Hubbard model is to think about this kind of spinning and Holon type objects. But in 1D, we said that, oh, they completely separate, they're unbound. Whereas in 2D, we actually think of them as being bound by a string, because when a Holon moves away from the spinon, it creates a string of flipped spins, and the magnetic energy scales linearly with the system size. And it's very reminiscent of the way people think about mesons in QCD, where you also have two sort of subparticles. These are two quarks. And if one tries to separate them, there is a linear potential which grows, and that's why they're always bound. That's why we talk about confinement. So one can put this picture in to kind of like even more sophisticated wave function. Like the simplest way of thinking about this wave function is like consider like a spin, and like it's so slow that, okay, let's just freeze it, assume it doesn't move. Then as a Holon moves, right, it creates this configurations of flipped spins. And therefore, if we think about the motion of the Holon, we should mark not only the point where it is, but actually how exactly it traveled, how it arrived at a given point, because this determines the nature of the strings. And that's why the kind of lattice in which we can think about the motion of a Holon is this complicated beta lattice, because it labels not just positions of the hole, but rather all the string configurations available. And therefore, to understand the nature of magnetic polarons, what one can take is just solve essentially a problem of a Holon hopping on this beta lattice with a linear potential. Yeah, I'll not show you all the results of this calculation, but I'll show you some of the comparisons with the data. Okay, but coming closer to experiments, okay, we already saw this construction of strings, and notice this is already way beyond like 1 or 2, like 2 or 3 point correlation functions. So it already relies on sort of analyzing like a whole image and trying to extract some useful patterns. So can we do this on actual data? So this is what Christy Chu and Annabelle have done from the data on the quantum gas microscope in Greiner scope. So how is it done technically? Again, I remind you that what we're looking at, right? Remember, like as a whole moves, it leaves behind these strings of flipped spins, right? So what we're going to do is look at all the images and try to look exactly for this pattern. Just try to identify this. In this case, you can say, okay, we're not yet trusting our neural networks to extract any patterns. We're doing it by hand. But we're already sort of analyzing data, which is sort of very rich in structure. So so one handicap, so in these experiments done in Marcus's lab, they could achieve the lowest possible temperature, but they could not yet have spin resolved measurements. So previously I showed you images from Munich where they could measure individually spin up and spin down fermions at the same time, but this was not available at that point in Greiner's group. However, it's not a showstopper. So the way to think about it, let's say we have a configuration, a snapshot, where we have spin up, spin down particles. Here they're blue and red. Sometimes we have doublets, right? This is the virtual ones, but again, just as I discussed before, there's technical issue doublets show up as empty sites. And then in the experiment, they have to choose whether they image just spin down, let's say the blue particles, or just spin up, the red particles. Let's say here they chose to image the blue particles. Then they measure all the spin up particles. And what they do, they want to find the string. So they sort of compare it to the perfect checkerboard, like the best. So there are two checkerboards, so they just find the kind of the closest one. And then they compare like like this specific configuration which they saw, how does it differ from this perfect checkerboard? And the difference with the checkerboard is exactly can be thought of as being a collection of strings. And here you can see that there is a string of length 4, string of 2 strings of length 2, and 1 string of length 1. And so then you plot a histogram, right? So that's just from a single shot. We already saw so many strings. And obviously this is done many times. So there are many snapshots, and okay, they again analyze all these differences with perfect checkerboard and construct histograms. So one caveat is I sort of introduce strings as resulting from the motion of the holes, but in reality, because experiments are done at finite temperature, even thermal fluctuations lead to existence of some flipped spins. So as a result, we have to deal with, like even if we take a system at half filling, no holes yet, we already see some distribution of strings, sorry. This is this blue point. But what we're asking is, well, as we add the holes, as we start doping, you see this as these blue points, the number of strings, especially long strings, goes up. Notice that the vertical scale is actually logarithmic. So here the increase is almost an order of magnitude. So there is an appreciable difference in the number of strings. And you can say, oh, but maybe it's just because when we added holes, we removed some of the sites. And of course, okay, like let's say a missing fermion just shows up as an extension of a string nearby. So you can ask, well, what? Maybe this is just a result of like this randomly sprinkling holes. The answer is no. Like, so this would be the yellow line. If we just took a system at half filling and just randomly added holes, we would only slightly increase the number of strings. Like the dramatic increase in an experiment is really due to the hole motion. And you can make it more quantitative. So again, this is a probability of having a string per site, and this is what we have at half filling. You see it's finite. This is our kind of like background. We're measuring signal on top of the background. This is what the holes add, and this is what we would get by randomly sprinkling these holes. So clearly we need we need to actually add this the motion of holes, how they sort of scramble spin configurations in order to explain the data. And this green line actually shows the prediction for the string distribution based on geometrical string models. So you can see that actually we do have actually a very good agreement between this model of magnetic polarons as sort of bound states of spin-ons and holons with experimental data. Okay, questions here? Okay, so so far we okay, now we can ask, but is there any new insight that we're learning that really helps us to like from this quantum gas microscope data that really helps us to explain some of the puzzles in cuprate? So let me try to show you at least one of the things which we're very excited about. So this is a canonical phase diagram of cuprates. Again, I will not go into the details, but roughly like doping on this horizontal axis is how many holes you add, like how many fermions you remove from this two-dimensional Fermi system. And it has, okay, so there is a superconductivity, exotic superconductivity, which people are very intrigued by. When there are no holes, we have antiferromagnetic state, and there are some complicated regime in between. But that was kind of the prevalent way of thinking about the phase diagram. So I'll not define it in details. I'll just, like, what's relevant to me is that in the last couple of years, people started saying, well, actually, this canonical phase diagram is not sufficient. There is some actually sharp crossover, like close to half filling, close to optimal doping, in which system on the left and system on the right look different. And you can see this difference if you look at like transport measurements in Nernst effect. You can look at some kind of charge correlations, or you can look at spectral function of fermions. So the question is, well, where does this crossover at small, like, so we have two regimes for strong doping and weak doping, but what underlies this? Well, let us look at experiments from the quantum gas microscope. What do they tell us? So I'll just show you some of the data. So what was done here, the first step, well, let's just look at the usual two-point correlation functions. And let us focus on just sites which used to be ferromagnetically correlated at half filling, you know, like in this case, this was diagonal. And now you can see this correlation as a function of doping. So, okay, at half fillings, they're ferromagnetically correlated, but then as we increase doping, it changes to anti-ferromagnetic correlations. We take other two sites, right? In this case, and this is sort of next nearest neighbor, but all in the horizontal direction. Again, this is ferromagnetic at half filling, but as we dope this system, the sign of correlation changes from ferromagnetic to anti-ferromagnetic. We take sort of even longer range correlation, but still like at half filling, the one that would be ferromagnetic, and again, it changes sign, and they all change sign at approximately the same doping of around 30%. Then we can also take these real space images of correlation functions and convert them to momentum space correlation functions, which is what we're used to neutron scattering. And we see that at the same doping, the nature of correlation changes from one which has a single peak at pi to something that has, you know, like the split peaks, and that's called incommensurate spin fluctuations. Okay, but these are two-point correlation functions. Well, actually, you can look at three-point correlation functions. So in this case, what one is looking at, it's like takes a hole and spin correlations in the vicinity of a hole. So these are really kind of spin correlations conditioned on being close to a hole. It's really polaron correlations. Again, we see a dramatic evolution. So like close to half filling, we have correlations which, like a hole would always introduce correlations that are opposite to what one would get in an unperturbed antiferromagnet. Say nearest neighbor would acquire extra ferromagnetic correlations, they are positive, but this only happens next to a hole. I remind you, it's really extra polaronic configuration, or let's say diagonal correlation, which away from the hole were ferromagnetic. Due to the hole, they acquire ferromagnetic component. So here we can see this is like really a signature of magnetic polaron, but then as we go to much larger doping, actually all the additional hole-induced correlations appear to be anti-ferromagnetic-like. And that's something that we expect for the Fermi liquid, because for Fermi liquid, essentially, well, all there is just like Pauli principle. If we have two fermions, they are much more likely to point in the opposite direction, and therefore, and sort of at any distance, we expect to see anti-ferromagnetic correlations. Here, okay, you can again see this sort of change of sign of like 3-point correlation function. So another kind of curious way of analyzing the data, but in terms of distribution functions, in this case of uniform magnetization, right? So what was done in these experiments, so this our images, like blue a spin down, right, a spin up, right? Okay, empty is a whole site. Then in any single shot, we can measure magnetization over a certain region, say within this radius R. But we know it will always fluctuate, like from equally likely to, like on average, to have up or spin down. But we can look at fluctuations in magnetization and then use fluctuation dissipation theory. And that actually gives a spin response function. And it turns out that this is a kind of a telltale sign of the pseudogap regime, that it actually really undergoes very strong change close to half filling. And indeed, what we see in the data is that far away from half filling, like by analyzing the sort of just fluctuations, like really noise and of magnetization in a finite region, we extract spin susceptibility, and we see that it follows like picture of weakly interacting fermions. But then it's actually saturates, and it doesn't really show us like a true pseudogap, or it would have to go down. But this is a result of experiments which are not yet at the lowest possible temperature. But all of these sort of points, okay, and maybe the last piece now, I sort of showed you 3-point correlation function. One can even analyze 4-point correlation function when we have two holes and two spins in between them. And in particular, in this case, what was found in experiments is that this correlation at larger doping look exactly the same way as what has been established for Cooper pairing, say, in ladder systems. So when we look at this higher order object, if two holes are next to each other, they really create spin configuration around them as if they make a sort of this kind of antiferromagnetically paired Cooper pairs. Okay, so all of this is suggesting that indeed this crossover that has been seen in cuprates, and it is also present in the kind of plain vanilla Fermi-Hubbard model. And it's really just a crossover from the liquid of magnetic polarons to a Fermi liquid-like state for larger doping. Okay, any questions?
I have a question.
Sure.
Your crossover, well, so there is number 1, 2, 3, and 4.
Yes.
Are any of these points, you know, can we rationalize by, you know, why that has to happen, like upon doping?
Okay, so what's happening for very large doping? That's natural. That's from a liquid, right? So the idea is that, like in essentially in whatever we see at large doping, we can get away with just doing simple RPA. Okay? Right. We can do like slightly more sophisticated version of RPA. So we see that it's weakly interacting from a liquid. So then what happens on the far left if we just have polarons which do not overlap with each other, right? That again we can rationalize because we have a model of individual polarons.
Right.
So what we have, so like a kind of a trend why it goes from a liquid like to something like a liquid, like a dilute gas of polarons is that makes sense. But the quantitative theory of sort of the crossover, that's much harder. And I also sort of have to admit that so far experiments are not yet at the lowest temperatures. So let's say while we start seeing these kind of polarons overlapping with each other, it's still too, like the system is too hot for this, say, for the self-organization of these polarons into either stripes or Cooper pairs. I mean, we see that if they're close to each other, they seem to make a spin configuration as if it was a Cooper pair. So it's like if you capture two holes nearby, well, they're likely to be in a configuration like a Cooper pair.
I see. Thank you. I encouraged people to ask questions. There is another question. Should this be some analogy to the quantum critical region that's been established by studies of moth metal insulator transition?
In a sense, yes. I think that is still I mean, like clearly, yeah, this crossover coincides with where we see this kind of strange metal behavior. Now, transport, I mean, in a sense, well, the approach taken here, right, was very different. It's not, we're not writing field theory for the strange metal, but rather we're trying to learn from experiments. So let's say the model of polarons is somewhat phenomenological because we're taking as much as we can from experiments, such as, say we take spin, so the nature of spin configuration, right? So that we construct the magnetic polaron, like remember this kind of motion on a beta lattice. So like say the string tension we take from results at half filling. Well, actually in that case, we could also take Monte Carlo. So, I guess you, yeah, so that is a difference. We're not trying, we believe that it's connected, but to really go from this kind of more microscopic picture, which is based on the polaronic liquid, to field theory, that's something that we have not done yet. But it's obviously a very interesting question. Okay, so maybe then just to come closer. So, okay, we already saw how much more interesting information we can extract from the data from the fact that every particle is measured simultaneously. So our images, sorry, experimental data, actual images. So the idea that Annabelle and Fabian started exploring was, well, and that's something that you already heard about from Una's talk, and I'll connect to Una's talk later on. But as a first step here, well, can one just do something very simple and try to say, okay, well, let's use standard techniques and let's try to explore whether neural networks can tell us which theories are better for explaining experimental data. And so what Annabelle and Fabian have done was they took sort of two models. One is a geometrical string model, which I described to you before, and where we assume that every hole makes a magnetic polarons, and then we just put them next to each other. Another is one of the commonly used mean field theories, called pi-flux RVB. So the biggest difference between them is that the geometrical string model, it really takes into account the fact that string configurations are perturbed in the vicinity of individual holes. Whereas the RVB theory is much more mean field. It says, oh, you know, holes suppress antiferromagnetic correlations, but they suppress them in the system as a whole. So this kind of, this model does not take into account this very local nature of sort of spin charge correlations. And then, okay, so we have two theories and we have experiments. So we have three ways of generating snapshots. And then what they have done was, okay, you sort of train neural networks, and that's something that has been discussed before and will be discussed extensively in the school. So I'll not go through the details, but this is sort of traditional CNNs using TensorFlow. We're sort of basically almost not looking under the hood. We're not asking, okay, how do they operate? Just use them as a kind of as a tool. And so in the first sort of set of comparisons, Annabelle looked at snapshots generated, like basically train the networks on three data sets separately, right? Experiments, geometrical string, and pi-flux. And what you can see is that neural networks were always efficient in distinguishing pi-flux from the string pictures and from the experimental pictures, which suggests that while this pi-flux data was fairly different from the other two. on the other hand, like actually separating between this kind of geometrical string model and experiment was could be done, but not very well, which means that geometrical string is actually sufficiently close to the actual experimental data. Then the other approach was to, well, let us actually train the data only using theory, right? We have a pi flux and we have this geometrical string. And then once the network is trained, let us bring experimental data and ask to which theory will it be assigned. And what you see is that experimental data until fairly large doping is much more predominantly assigned to the geometrical string, which again suggests that geometrical string is much closer to is a better description of experimental data than the pi flux, which suggests that this local correlations between charge and spin are actually crucial. And again, you may be skeptical. Well, why is it only 15%? And I want to emphasize that this comparison is done like on a single snap, like these numbers are given for a single snapshot, which has very limited field of view. It's like, okay, we're talking about like 8 by 8, say, field of view. If we, let's say, take a few snapshots, say 4 snapshots from the same category and say, oh, okay, we know that all of them must be from the same, must be this sort of generated the same way, then like this slight imbalance for a single snapshot immediately becomes like a much larger imbalance, like a much stronger statement when we talk about all 4 snapshots. But of course, the disadvantage of this specific project was that it wasn't clear what exactly was CNN doing in order to distinguish different theories. And this is when collaboration with Cole and Una has started. And that's what you heard about from Una's talk in the morning, when she told you about designing neural networks which actually can be which are interpretable, which really tells us which correlations are physically relevant. And now you can see that what we learned is that the correlation which were meaningful to us, like how geometrical string were analyzed, were really like configurations that can be related to, imagine that we start with some spin configuration and then a hole moves and it scrambles a spin sort of configuration next to it, like say configuration like this, and and then a hole moves to the neighboring side. I think with this my time is up. So this is the conclusion. I try to sort of show you a little bit of a historical perspective, how sort of people started looking beyond 2-point correlation functions from the very early days of experiments with cold atoms, and how this analysis of multi-point correlation function, distribution functions, and even like looking for pattern are taking central stage in the analysis of results from quantum gas microscopes. But then there are also other types of cold atoms experiments. So it's really kind of wonderful, promising new kind of direction, experimental direction for exploring, for using the tools of data science, such as machine learning, neural networks, and so on. Thank you.